And to kick things off, I'd like to introduce our first honored guest, Patrick McCorry. Now, I'll do a quick intro. The first time I had really come to know of Patrick was because of a rather particular shared affinity on Twitter. Patrick sports a unique profile picture. It looks like a CryptoPunk, but it isn't a CryptoPunk. What is it? It is what the NFT Twitter community calls the bastard gang punks, or bastards. So off the bat, I already feel a deep shared connection to Mr. McCorry. But upon further inspection, beyond the NFTs, one may find it easy to find Patrick a likable, self-humoring individual. On LinkedIn, his official title tagline is "When Moon Advisor." More notably, he has an extensive academic background from stints in Newcastle University, University of Illinois at Urbana-Champaign, London's Global University, and King's College London. He's also distinguished as the UK's first PhD graduate in cryptocurrencies. He became well known for building Any.Sender, a non-custodial service for outsourcing transaction infrastructure, before it was acquired by Infura ConsenSys, where he is now working as a software developer. More recently, he caught crypto Twitter virality, something we're all after, by doing the very permissionless thing. He gave out and completed a free cryptocurrency course taught in the style of a Master of Sciences module, teaching everything from cryptography to distributed systems to mechanism design. Now, I can't quite recall the numbers in attendance for the course. Patrick, you might be able to tell us more, but I do remember that it made its rounds on Twitter, garnering non-trivial amounts of attention and registrations. So without further ado, and to prevent myself from stealing more of your thunder, I'd like to invite Patrick McCorry up to the stage, into the screen, to give us his next lecture on bridges and layer 2 protocols.
Awesome. That's the most extensive introduction I've ever had in my life.
I love doing that.
Cheers, guys. I can get started, I guess. Let me just share my screen. Yeah, just before I get started, I feel like given the quantity of people here, what might be nice is I'm going to try to treat it as a bit of a workshop. So I don't really want to treat it like a talk, because I don't really want to lecture people for the next half an hour, because that's pretty boring. So basically, as I go through this, if you have any questions whatsoever that are related to the, oh, my sharing's paused, one sec. Let me just fix that again. There we go. That should hopefully be better. Okay. So basically, if you have any questions whatsoever, just stop me halfway through and ask the question. It could be about this talk, or it could just be really about anything, whatever floats your boat. So, yeah, so what I want to give a talk about today is a note on bridges and layer 2 protocols. What I want to give is sort of the motivation for why we should care about layer 2 protocols, and a breakdown of how they work under the hood, but without going into the nitty-gritty detail. What are the problems that you need to solve for these systems to work? So let's just get started then. So as most people here are aware, cryptocurrencies don't scale. Bitcoin supports on the magnitude of 10 transactions per second. Ethereum supports 15 transactions per second, give or take. And as we're all aware, when the fees skyrocket, actually when the network is congested, the fees skyrocket. So a couple of years ago, I used to say that the fees on Ethereum would go from a penny to $1. But nowadays it goes from like $1 to $400. Maybe give an emoji in the chat if you've ever paid $400 for an Ethereum transaction. It's a bit outrageous sometimes. No one wants to pay that amount of money. And there's always someone though. There's always someone who has. So then, can we fix this problem? Can we build a network that's affordable and scales at the same time? And this is what like other networks promise. So like Polygon's proof of stake protocol, they promise 7,000 TPS. Solana promises 65,000 TPS. Although Solana struggles to stay online, to be honest, it's always offline now. But that's another problem. And Avalanche as well, Avalanche claims to support 4,500 TPS. And obviously, in these networks, the fees are cheap. Solana didn't actually have any fees for about a year. Then they just reintroduced it recently. So clearly we can already build these networks with low fees and high throughput, and we've solved the problem. So why do we care about layer 2? Why even bother with this talk? Let's go outside and get some pims. No, I'm only joking. Clearly the problem hasn't been solved. And the reason it hasn't been solved is because when you think of the layer 1 network, something like Bitcoin and Ethereum, the goal is that there's this off-chain database that has all of our account balances. And the goal is to get this database and spread it as far and as wide as possible. So everyone can have a copy of the database, everyone can audit the database, and everyone can verify that the database is okay and good, because at the end of the day, it records all of our assets. And this is really at the heart of what it means to be decentralized. Regardless if you're in India, the US, Argentina, Russia, New Zealand, regardless where you are in the world, there should be a certain percentage of the world's population who could download the blockchain, who can recreate the database, and they can verify themselves that the database is correct and valid. That's ultimately the goal here. But the issue is that because we're targeting a percentage of the world's population to verify blocks and transactions in real time, what we've ended up doing is artificially constraining the network's resources. We've artificially constrained the CPU, the storage, and the bandwidth. And so what we really ended up with is a computer from the 1970s. It's slow, expensive, and everyone has to share it, including baby Vitalik. That's Vitalik and his old computer, and that's probably more powerful than Ethereum. We've basically artificially constrained this computer. So if we care about decentralization, then should we just give up on scaling? Should we just give up on the goal of trying to have high throughput? And clearly not, because there's a trade-off. If people can't afford to use the network, then they're not going to download the database and verify that it's correct. So there's a trade-off between how much we can scale and also trying to keep the network affordable for most people in the world. And again, guys, if there's any questions, just stop me. You can just chip in and just interrupt me at any time. So scalability really means is that, can we increase the transaction throughput of the system while still adhering to the same set of resources? Given the constrained resources, can we still increase the throughput? That's sort of what we mean here for scalability. But there's a third way. And the third way is basically saying, okay, we accept there is this network. It's not very efficient, it's quite expensive, but this network holds all of the assets. Right now it has hundreds of billions of dollars locked up in assets on this network. Could we build a system where we could take the assets, lock them, and then unlock them on another network or on this off-chain system? And if I could, lock the assets into an off-chain system, then maybe I could just transact there instead. If I can transact on the off-chain system, then I don't actually have to use Ethereum, but I can still use the assets that reside on a network like Ethereum. So the idea is really taking transactions away from the main chain. That's the goal with these layer 2 protocols. Sorry, go ahead. Does someone, I thought I heard a noise. Okay, cool. I'll just continue. So that's the goal anyway. So before I continue, who's ever used an exchange before or an online service? Who's ever used Coinbase, Binance, Bitstamp? Who's ever, I guess most people here have probably used a cryptocurrency exchange before. Yeah, look at the thumbs up. So, so what's important to remember is that historically speaking, for the past 12 years, the main use case for cryptocurrencies like Bitcoin, Ethereum, and even Tron, because Tron does have like billions of dollars of tether on it, it's really this interruptibility solution between the exchanges. I'm on Coinbase, maybe that's where I buy my crypto. Then back in the day, I transferred to Binance because I want to gamble on some shit coins. That sort of was one of the big use cases for cryptocurrencies. And crypto was the rails that connected all of the exchanges. But the vast majority of transactions occurred off-chain. They occurred on these centralized exchanges. And that's how we've scaled the network for the past 12 years. But the problem is that these exchanges, they're fully custodial. They can freeze, confiscate, or lose our funds. And we also can't audit the systems. We have no idea if, the Coinbase, I'm just saying Coinbase as an example, not to point them out. Coinbase has a database that describes all of our assets. That's like the liabilities. And on these cryptocurrency networks are the assets. And we have no idea if the assets held by Coinbase can cover their liabilities. We can't audit that. We can't check that. We have to blindly trust these exchanges to protect our money as they're locked in the system. So at the heart of all this interaction, what is at the heart of this type of interaction with a service like Coinbase? And it's really bridge engineering. That's all we've been building for the past 12 years, or bridges. And you can imagine that, on a network like Ethereum, there's a special bridge contract. And the bridge contract will hold the assets that are used on Coinbase. And Coinbase is a single authority that has custody and control over all the assets held by the bridge. So if Alice comes along and Alice wants to, and you can imagine this bridge contract has certain functions, maybe a deposit function, a withdrawal function, an allowance function. Then Alice comes along and Alice could say to Coinbase, Coinbase, I want to withdraw 1,000 ETH from the system. What typically happens is that Coinbase would authorize this, send it to the bridge, and then later on, actually the bridge would then get the message from Coinbase and say, Alice wants to withdraw 1,000 ETH. This was approved by Coinbase. As the bridge, ICE accept that Coinbase is trustworthy, and they're attesting to the fact that this off-chain database is correct and valid. And then afterwards, Alice can come along and withdraw her ETH from the bridge. And that's sort of the interaction that's happening here. What you could, generically speaking, there's an off-chain database that has the account balances, the program state, everything else. And there's a bridge contract that holds all the assets. And the trust assumptions really is that the smart contract needs to be confident that this off-chain database is okay before it will process a withdrawal. Because after all, it wants to make sure it can cover all the withdrawals. Now, over the years, how we've protected this off-chain database has evolved. For most systems, we typically trust one authority, the one ring to rule them all, the Coinbase or the Bitstamp. We trust the one authority to protect this off-chain database. Then we started thinking, could we have a multi-authority system? Maybe there's some consensus protocol, maybe we need KFM parties to approve it. So as long as a majority of the parties agree, then the bridge will allow funds to be withdrawn because they trust the majority to protect the database. And over time, we've had these sort of crypto economic bridges emerge, and they come in different shapes and sizes. But the idea is that there's no set of parties who can be appointed to protect the database. So what if I could appoint myself? I'm willing to lock in $1 billion. I have skin in the game. I will then elect myself, and I will elect myself to protect the database of other people. And that's basically Polygon's proof of stake bridge. And when you look at it, this is taken from a snapshot in 2021. About 6 entities in total, work together to protect the off-chain system. If they collude, they can steal all the money from the bridge. But obviously, they've put skin in the game. They want to protect the database. So that's why they've locked up so much funds. So here there's 6 parties, but they've self-appointed themselves to protect this database. But the problem of all of these approaches is that it sucks to trust a third party. The whole point of cryptocurrencies was that, even the Satoshi Nakamoto quote, the root problem of conventional currency is all the trust that makes it work. We want to minimize trust. We want to remove trust. We want to remove these intermediaries altogether. And there's many reasons for doing that. It's not even just that they're that we have to trust them out of an ideologically speaking. It's because it's just so difficult to protect billions of dollars. So these are exchange hacks over the years. Mt. Gox lost 850,000 Bitcoin. Bitstamp lost 19,000 Bitcoin. And it's not because they're malicious, they're just incompetent. It isn't even that they're incompetent, it's just so difficult to secure billions of dollars. It's not a very trivial job. And even the multi-authority bridges we saw with the Ronin bridge, they lost, what was it, $600 million. Although 4 validators were basically one company, and that one company could authorize other people to do stuff. But basically they didn't implement it very well. And even these crypto economic bridges, so this is an example of beanstalk farms being hacked because of a flash loan. Not necessarily a bridge, but the same idea that even if you have this crypto economic bridge, it can still be abused and hacked. So the problem that we've had with all these approaches to building an off-chain system is that we forgot about the old school motto, not your keys, not your coins. It's very Bitcoin oriented, that quote, but we forgot about the idea that we should have custody of our own funds and we should sign transactions and only with our authorization should something be done or be allowed. So the question is, can we build an off-chain system like Coinbase, for example, while still allowing users to maintain self-custody of their funds? And this was the goal of the original sidechain paper in 2015. They don't really mention the word bridge in the paper, but what they were actually building was a system where on Bitcoin, I could lock up my Bitcoin and then unlock it on another experimental blockchain. I could then transact there as much as I want and then move my funds back to Bitcoin. It was a two-way peg. It's basically a bridge that relied on SPV proofs. But at the heart of it was trying to build this trustless bridge. But the issue was that I would call this a consensus bridge, because what the bridge relied on was the fact that the consensus protocol of the experimental blockchain was alive and well. And a consensus protocol, at the end of the day, is just a set of parties. You know, we're trusting a consensus protocol with a set of parties to allow that chain to continue and make progress. And this is sort of similar to the Near Rainbow Bridge. They also have this sort of consensus bridge between a Near and Ethereum. So, you know, they've tried to implement it, but the problem is we have to trust the just, you know, the bridge from the perspective of the bridge, it has to trust and follow the judgment of the off-chain system consensus protocol. And the issue there is that if the consensus protocol goes offline, for whatever reason, your funds get stuck on the experimental blockchain. And two, if the consensus protocol agree to an invalid transaction, then the bridge could still be hacked and lose all the funds. So we still haven't solved the problem, you know, but can we really build a bridge that protects us from an all-powerful authority? And that's the goal of these rollups. You know, the Arbitrums, the Starknets, the Optimisms. What they're trying to build is a validating bridge. And the idea is that the bridge can independently verify that this off-chain database is alive and well, you know, that its integrity is intact, it's continually making progress. And if anything goes wrong, the bridge has the power to force progress and to force updates to the database. And so this is sort of what all these companies are trying to build. They're just trying to build a really nice bridge where you don't have to trust a set of authorities with your system. You know, all the different layer 2 projects that are doing that today. And again, the whole point is that the bridge can independently verify the correctness of the off-chain database. Because at the end of the day, the off-chain database records all of our balances. It's the liabilities. We want to make sure that is correct. Go ahead.
Patrick, one question here. This is Jam. When you talk about the bridge, is that like an entity, or are we talking about smart contracts?
This would be a smart contract on Ethereum, for example.
All right. Okay.
It could be implemented as a multi-sig for a lot of the early systems, you know, or, you know, but basically, generically, it ends up being this smart contract.
Okay.
Yeah, and this is really important. So I'm actually writing a blog post about this right now, is the mental model to think about it. In a layer 1 system, the mental model is that we want this database to be broadcast as widely as possible and for a super majority of people to agree that the database is okay and well. So that's a layer 1 system. A layer 2 system, the mental model is that it's only the smart contract that cares if the off-chain database is okay. You know, if the off-chain database is invalid, the smart contract will reject it, and it doesn't make a difference. You know, so it's actually a very different mental model to a layer 1 system and a layer 2 system. It's much more like an exchange or like an off-chain service that already exists. That's what we're comparing it to. So, but ultimately, the goal here is that Ethereum, the layer 1 blockchain, the smart contract, is protecting your funds and not a trusted set of funds. You know, a bit like Mayweather punching this guy. I don't actually know who that guy is, but I just found the picture on the internet. You know, if someone wants to censor your transaction, bam, Ethereum doesn't let that happen. If they try to include an invalid transaction on the database, bam, rejected. If they try to withhold data from the database for you, rejected. You know, it's fighting in your behalf to make sure anyone can get access to the database. Of course, there's also the marvels of engineering. If you look at all these layer 2 projects, they're building just different type of bridges. You know, you have the tilting bridge, the longest bridge, the most famous bridge. Actually, the longest bridge, that isn't the case anymore. The one in Zhuhai to Hong Kong is the longest bridge. But anyway, you know, everyone's building different type of bridges. But this sounds really cool. But then how does it work under the hood? You know, how do we actually build a validating bridge? So I'm briefly going to describe, you know, here are the agents, an overview of how it works, and then the, you know, the threat model and some of the security properties. And I'll go over this fairly quickly because obviously I don't want to, you know, take up too much time. But anyway, so there's three agents. We have the honest party. She likes mooncats or maybe bastard punks, you know. Honest user just wants to trade some NFTs. You have the sequencer. You know, the sequencer's job is basically to take a list of transactions, order them for execution, and then tell the bridge, these are the transactions that should be executed. And then we have an executor who will take these transactions, process them, propose an update to the database, and then convince the bridge, you know, given those transactions, this is how the database should be updated. You know, they all have very separate roles. So how does it work at a high level? So the idea is that a sequencer will post these little checkpoints to Ethereum periodically to say, you know, this is the list of transactions that should be executed. Alice will come along and Alice will deposit one coin into the system. She will send it directly to the bridge and it should show up on the off-chain system eventually. Bob comes along, hi Bob, and then Alice wants to transfer coins to Bob on the off-chain system on the layer-2. So you'll sign the message, give it to the sequencer, and the sequencer can pass this on to Bob to say, Bob, you know, I've got this transaction. I will order it for execution very soon. But, you know, for now, you can be notified to say this will probably get confirmed okay. A bit like, you know, using Coinbase. We wait around for a while, then eventually the sequencer will post a list of transactions to Ethereum, to the bridge, and then the bridge will be aware, okay, you know, these are the list of transactions that are going to get executed. And then we wait around because the transactions are ordered for execution, but they're not yet executed. And then we come along, the executor takes those transactions, he'll execute them, my wonderful 1990 animation, and then they'll send an update, you know, they'll propose an update to the database, they'll send that to the bridge, and they have to include evidence that this update is valid and correct. And this happens, you know, in a continuous cycle. You know, we propose some transactions to execute, we propose an update to the database, and every epoch, you know, the bridge is being convinced that every update to the database is valid and correct. And that's all that's really happening here for a layer 2 system. Now, of course, when you go into the detail of how this is implemented, you know, they're all slightly different, but this is roughly what they're all trying to achieve at an abstract level. And of course, because all the transaction data is public in the bridge, then anyone can get the transaction history, anyone can recompute the database, and anyone can also independently check that the database is okay and well. You know, that's the data availability problem that I guess you guys spoke about last week. You know, the whole point there is that we want to guarantee that anyone can compute a copy of the database, so the data has to be publicly available, and the bridge guarantees that. Okay, so that's how it works at a high level. What's the adversarial threat model here? So the adversarial threat model is fairly straightforward. Alice can send a message on the layer 2 system, but the adversary can view, order, and drop all messages on the layer 2 system. Basically, they control the ordering of all messages. The only guarantee an honest user like Alice gets is that she can send a message to the bridge on the layer 1 blockchain. That's her only guarantee for message delivery. The second one is that we can only assume that Alice and the bridge are honest parties. Everyone on the layer 2 system, you know, all sequencers and nearly every single executor can be corrupted by the adversary. So we're basically assuming this entire layer 2 system could be adversarial, and its only goal is to steal all the funds on the bridge. You know, that's like a crazy adversarial model. You know, they can control all messages, nearly everyone's corrupted. The only thing they can't do is break cryptography or break the bridge. And when you get into details from some of these layer 2 protocols, not every protocol can really beat this adversary. You know, it's actually a very difficult beast to beat. And this is actually, I guess, oh, go ahead, Sam.
Sorry to interrupt you, but one question: the executor is something on the layer 1, right? So executes the smart contracts. Is it?
Well, the executor's off chain. So if you think about like Coinbase, for example, let's consider them as an example. On Coinbase, you're on the user interface. You authorize a swap. When you give that swap to Coinbase, you can imagine there's like a sequencer there who's basically just collecting all the trade transactions and making sure they're in order. Then they'll notify you to say all your transaction will be executed. Later on, Coinbase will give this to a set of executors who will then propose an update to the database. So it's like a two-step process: order the transactions, execute them, and then tell the bridge that, you know, the database has been updated and the update's valid. Cool. So ideally, the layer 1 blockchain, the smart contract, should do minimal work. It doesn't want to do any work because it's too expensive. Everything happens off chain. Cool. Okay, so then there's this wonderful quote by Georgios, where he basically says that, what makes layer 2 special is that layer 2 security equal layer 1 security. In an ideal world, when I'm interacting with Starknet or Arbitrum, I shouldn't have to trust any of the parties on that system. I should get the same security as if I was just transacting on Ethereum itself. And that's sort of the idea behind scalability there. We transact off chain, but we keep the same security as if we were transacting on Ethereum. But what I typically argue, and obviously this is the whole point of the talk, is that it's very difficult for layer 2 security to equal layer 1 security. But we can get pretty damn close. It can get so close to layer 1 security. And it's really this closeness that everyone's debating when they talk about, like, optimism or optimistic versus EK, for example. They're really debating how close they can get to Ethereum security. But they can get pretty damn close regardless when you zoom out a bit. So what are the security properties? What does it mean for a validating bridge to protect our funds and to protect the database? So remember, our only goal is that there is this off-chain database that we've all locked our assets into, and we want to protect its safety. Every update is valid, and its liveness, such that if everyone in the layer 2 system goes offline, we can still keep updating the database and we can keep making progress. Maybe I want to withdraw my funds, so I can force an update on the database eventually and get my funds out of the system. If everyone goes offline, I'm still okay. So there's 3 goals here to achieve this. One is the data availability problem. And the best way to think about it is that from the bridge's perspective, is the bridge convinced that all updates to the database are publicly available? Can anyone get a copy of the database? That's all the bridge cares about. Remember, no one else cares about this, only the bridge. And then the second one is the state transition integrity property. The bridge wants to be convinced that every proposed update to the database is valid and correct. There's no invalid transaction that steals everyone's money. And finally, censorship resistance. And that's the liveness idea. If the operators on the layer 2 system are malicious and adversarial, can an honest user still get their transaction executed and eventually exit the system? There's the 3 goals to achieve all that we want. So the availability problem is fairly straightforward. Can we guarantee, all updates to the database are publicly available? And there's several reasons why you want this. 1, I want to audit the database. 2, I want to interact with a smart contract. It would be good to know the state of the smart contract. And 3, I may need some data to withdraw my funds from the system. I need to check if my Mooncat is actually on the rollup before I withdraw my Mooncat from the system. And bingo. The way we solve this problem, there's 4 different ways, and I'll just talk about rollups, is the way the bridge is guaranteed the data is publicly available is that all updates to the database are posted to Ethereum. The bridge itself will literally get all the data and then throw it away. It's in the blockchain. So as long as the bridge is aware the data was available, because it was posted to Ethereum, then it's convinced that anyone can get a copy of the database. So that's the idea of a rollup. You're rolling up the data and just posting it to Ethereum. So what about the state transition integrity problem? So the idea here is that we want to make sure that every proposed update to the database is valid. And obviously, if the adversary could include an invalid transaction, they could steal all the money from the system. So obviously, we don't want that happening. And bingo, this is where you get the optimistic versus the ZK, the fault proofs versus the validity proofs. You know, I won't go into the detail for this today, but the point I want to make is that the whole idea of a ZKVM, the fraud proofs, the validity proofs, is only solving this one problem, guaranteeing that every update is valid. You know, it doesn't really solve any other problem in the system. It's only this one very narrow problem is solving. But it's also the one that's discussed the most because it's the hardest to solve. And then the last one is censorship resistance. You know, what happens if the sequencer is not cooperative and they don't let me withdraw my funds? You can imagine it's a bit like Coinbase support. You know, they always like lock up your funds and make you submit a support ticket. Now, when I want to, you know, withdraw my funds and they're like, oh no, never. Aha, your funds are stuck forever. And I won't go into the details of the solution for this, but what's important to highlight is that the sequencer who orders transactions has absolutely nothing to do with censorship resistance. Their only job is to offer a good user experience, which is actually why when you look at Arbitrum or Optimism, it's actually fine that the sequencer is fully centralized because they have nothing to do with censorship resistance. Their only job is to order transactions optimistically and, you know, get them eventually processed by an executor. If they go offline, then as we'll see, you can just take your transaction, submit it directly to the bridge. The bridge will order it for execution. Then later on, it gets executed. And so what we really care about is the set of executors. You know, who can produce the validity proof? Who can submit a checkpoint that could then, you know, participate in this fraud proof system? We have to assume there's one honest executor who will post an update to the database that actually does execute transactions. And that's and ideally anyone could be an executor. You just need one of them to be honest. But just to summarize, you know, we can solve the data availability problem, the state transition integrity problem, and censorship resistance. Then maybe we can slay the beast and deploy a secure layer 2 system. Now, this is a picture from the bear wheel in 2014, and I modified it with a Ethereum shield instead of Bitcoin. You know, it's this historical picture. But of course, there's other problems that arise, but that's for another day. The last thing I want to highlight is really what's cool about these rollups is that they do bring down the cost. You know, the V1 rollups for a Uniswap, the cost went from 120K gas to 5K gas. And now they're getting even cheaper, you know, so that's a significant saving for swaps. What I'm really excited about is that what we're really moving away from is, you know, the Web 2 world was the Binance, Bitstamp, Coinbase, and now we're going to build exactly the same services, but in a way where we don't have to trust the operator. And to me, that's sort of the whole layer 2 movement, is building a better Coinbase, where I could actually deploy a smart contract on Coinbase and anyone can interact with it. And I think this is going to work because, you know, custody is a liability for most of these off-chain systems. My final point is that, you know, when you look at all these cryptocurrency exchanges, they keep getting hacked. And that's because you have to take a set of human processes that will protect billions of dollars and scale that to thousands of services. And clearly that doesn't work because people keep getting hacked. There's very few exchanges today where you would say, oh, I'm willing to store like my life savings on that website. You know, clearly there's most people, I mean, I guess maybe most people don't care about it, but, you know, it's just a very difficult problem to solve. Where we get one roll up, if one team can get it right, and they can actually develop the software that works, that really does protect our funds. You can take this software and reinstantiate it for every single service provider. And now as a service provider, I don't have to take custody of your funds. I don't have to protect billions of dollars. I just run software and the bridge takes care of it for me. And so actually, I don't think users care about this at all. I think it'll be the operators that will drive adoption because no one wants to take care of billions of dollars. That's too much. That's stressful. You know, custody is a liability. So that's the end of my talk. Oh, I'll finish it there. So GG guys, is there any questions or is there time for questions? I don't really know what the time's like.
Absolutely, there's time for questions. Thank you first and foremost for that very lovely presentation and lecture. There's a question from Saif here. Saif, do you mind unmuting yourself to ask, or would you like me to read the question for you?
Sure. I was thinking about whether this executors and the sequencers can be decentralized. For the executor, I'm guessing a proof of stake thing and a random selection could happen, but I'm not sure whether that's possible for the sequencers.
I think for the sequencer, so really, when you think of, I guess that separate out the rules a bit. So all the sequencer cares about is transaction inclusion. You know, can I take a list of users' transactions and include it in the blockchain? If the sequencer disappears, you know, they're offline. All the user has to do is take their transaction and give it to the bridge directly. So as long as there's one honest party, I can always get my transaction included in the blockchain, you know, included for execution. So for the sequencer, there's no real benefit from decentralizing it as such, because I can always get my transaction ordered for execution. What you may want is like a fair ordering protocol. So maybe some consensus protocol where they can guarantee the transactions were ordered in a fair manner. And that's really to stop stuff like MEV. You know, the problem right now is the sequencer can take all your transactions, you know, extract lots of value and then post it, a bit like Robinhood. And that's, I know people like that, people don't like that. So a lot of people are looking towards, you know, distributing that out with a fair ordering protocol. For executors, you very much want that to be as decentralized as possible. For the ZK rollups, it's quite doable because it just involves posting a proof. And there's some nitty-gritty detail, I guess, that could be a bit awkward. For the optimistic rollups, the issue is that if you make it too decentralized so that anyone can do it, you could just have people submitting fraud. Remember, all the fraud proofs are interactive in these optimistic rollups. So they can just keep triggering these like fraud games. And then it takes like 10 transactions to go through a single game. And, you know, the game doesn't actually say if it was invalid or not, they just show who was wrong. So you need a rate limit who can participate in the fraud proof system, because otherwise you just end up with spam. So it's like a trade-off there between who should be able to participate, how much can you get slashed, you know, but it should be an open, at least an open membership group where anyone can participate if they're willing to stake funds.
Yeah, I suppose you could, you know, require a bond to submit a fraud proof. That could help. Another question I had was, it seems like when you have so many L2s, your liquidity and your assets become a bit, you know, you have 10 ETH here, 20 ETH there, and it seems to be a bit divided. I was looking at Seller Bridge and Hop Bridge, and it seems like when you transfer from one L2 to another, it's also a trusted bridge in between. Is there a way we could do it in a trustless manner?
Yeah, definitely. I think for this, I got 2 points for this, I guess. The first is that like I'm not too worried about fragmentation, because this is how most, you know, that's how the ecosystem is today. You know, assets are on Coinbase, Binance, FTX, you know, etc. So all the assets are already fragmented. The issue is that if I want to go from Coinbase to Binance today, I have to go via the layer 1. You know, I have to go via the bridge, and there's no real quick way for me to move my assets. What's nice about stuff like Connects, Hop Protocol, Seller, is that now people can start offering a service to quickly move your funds from one off-chain system to another. And that's never really existed before, maybe except for credit lines or something. So now we can start building these interoperability layers across the off-chain systems, which is really cool. It's never really existed. But as you mentioned, they're still trusted. A lot of them are still fairly trusted. This is actually why I'm a big fan of the Bitcoin Lightning Network, because Lightning is actually an interoperability solution. The whole point of it is that from one custodial database to another custodial database, I want to move my Bitcoins across in a trustless manner. Then, you know, the problem is they're all custodial right now, but you could easily see, you know, a connection on Lightning between Arbitrum and Optimism. And then that would be a trustless way to, you know, move your funds across. So it's just like, you know, TLCs basically, or atomic swaps. So you can definitely have like trustless solutions. But the only problem is everyone's tribal, and you know, Ethereum people don't like hearing about Lightning, and Lightning people don't like hearing about Ethereum. So there's this weird disconnect, even though they're building complementary things.
All right, thanks, Patrick.
I think Frank, you also had a question here. Did you want to unmute yourself to ask? Something about being reliant on exchanges as on-ramps from fiat. I wasn't sure. I'm not sure what that's in reference to.
Maybe it just means that you can't get rid of exchanges because they're a fiat, they're a fiat gateway to the ecosystem.
Right, right.
If that's what he means, then I agree. I mean, like the idea is that if I'm Coinbase, what would be really cool is that I can still provide a fiat gateway, but I just don't have custody of anyone's funds. Now I have custody of my own funds. And maybe I have some, like, I'm Coinbase, I have a big pot of Bitcoin. When you buy, when I sell you crypto, I just transfer you custody on my off-chain system. So then, you still buy crypto in a non-custodial way. I mean, I guess you're still trusting the fiat gateway, but you can still have that service, which is really cool.
Thanks for that. And then I think there was one more question at the very beginning. I believe it was from Chem. Can you shortly explain why there is a constraint? Again, I don't quite remember what that is in reference to.
It's to do with the transaction throughput, maybe.
Yeah, exactly. So, because you could basically you could just have a larger block size and so forth and so on, and I think there is a there's an idea behind it. Maybe you can just explain shortly.
Yeah, I can summarize it. Yeah, so there's this really good paper from 2016 that sort of explored this, and this paper was written during the Bitcoin block size wars, and the issue there was that what's the ideal block size for Bitcoin? Because obviously people want 1 megabyte blocks, 8 megabyte blocks, 20 megabyte blocks, a gigablock. No one could really agree on a value. So the way they tackled the problem was that, given the peer-to-peer network today, the peer-to-peer network is responsible for sending messages across the world. So every peer can get a copy of the transactions and blocks in real time. And so the goal is that as a peer, I should be able to get a block, update my database before the next block is minted and then sent to me. So I can process blocks in real time, and I can keep up to date, and I don't fall behind on processing the updates. So what they worked out was that back in 2016, if you wanted 90% of peers on the network to still process the blockchain in real time, you could support 4 megabyte blocks. It's probably a bit higher now, but that's the limitation is, what percentage of the current peers on the peer-to-peer network can actually process process updates in real time. If they fall behind, then there's no point them being on the peer-to-peer network. So that's sort of the scalability bottleneck there. Sorry, go ahead. There's a hand up.
Oh, hey, yeah, thanks for the presentation. I just had a question, like with respect to, composability. It's like, I wonder if it's almost kind of dishonest to call all these L2 scaling when you can't even like interact like with a contract on Optimism if you deploy it on Arbitrum, unless you're using like some other traditional EVM to EVM bridge currently. So yeah, I guess I wonder if you're aware of any progress made in that space. Because yeah, I don't know, it kind of feels weird to call it scalability because now we're just really having multiple blockchains at this point. Unless we have, we can call a contract from one rollup to another rollup.
Yeah, I feel like when you think about scalability, what it's really doing is moving execution off chain, but keeping the data on chain. So it's really saying that, our execution can't really scale on the network. So let's move it somewhere else and deal with it there. Then the real bottleneck for Ethereum today is data. If rollups really take off, then how much data can we process? And that's why you end up with like bank sharding or, even Solista's sharding approach. So then if you can shard it, then at least if I'm a peer in the network, again, my resources are artificially constrained. As long as I can process one shard, maybe I don't have to process all the data. You're distributing out the work amongst the network. But I also like, on the other hand, I don't like comparing L2 scalability to L1 scalability because they're two different problems. L2s are really architecture-wise are much more similar to an exchange or service, where an L1 is trying to build a network that ultimately protects this database. And so there's just two different architectures. And so I always feel that, not dishonest, I don't know, I just don't like to compare them because it's like apples and oranges.
Yeah, no, I think dishonest was a bad choice of words, but I guess, yeah, I don't know, I don't have a better, I'm bad with words, I just woke up. But yeah, it's kind of feels different than what I a lot of people envisioned scalability to look like, like 5 years
Oh,
ago.
definitely. I mean, people are definitely looking like execution shards and stuff and trying to maximize the network of what it's capable of. There was yet another question. I can't remember what it is now. What was like the last part of it?
Oh yeah, I guess. Oh yeah, I was wondering, since you're so into like this roll-up stuff, if you have seen any efforts in composability,
Composability,
in different roll-ups. Yeah.
So right now, it's fairly easy to be composable for, moving funds across blockchain. So if you're an Arbitrum and I'm an Optimism, you could have someone in the middle where I'm willing to take your funds in Arbitrum, then I'll also send you the funds in Optimism. And they're calling these like liquidity pools, where everyone locks up funds in this big pot, like a facilitate the transfer of assets. But being composable with smart contracts is in, maybe I want to, take a loan in Aave I never pronounced it right, on Aave. I take a loan in Aave on our Optimism, and then I take that loan, then I perform a swap on Arbitrum. Then on Arbitrum, I move over to Starknet and I do something else, and then I come back. And ideally, it should all be atomic. Either all the smart contract interaction works or it all fails. And I feel like there's very much a missing piece of research there. I don't think anyone's really looked into that in detail in a way to do it atomic. And that's just because it's an asynchronous process. By the time you set up the route, the middle one could fail on its way back. And I feel like there's actually like a really nice research paper just sitting there to explore that, but I've not seen anyone do that work. But yeah, so I think that's a good point about composability. Is atomically executing smart contracts across multiple chains is still an outstanding problem.
Thank you for those questions. I think Georgios, you have a question, and then maybe that could be the last one before we move on to Marius's presentation. Georgios, do you want to ask by unmuting your mic?
Yeah, sure. Yeah, I was wondering, what do you think about seeing many Optimism, Arbitrum, or any other rollup forks after they're stabilized, and if they become so successful, we start seeing so many of them as we saw with Uniswap forks, for example?
I love to see it. I mean, ideally, the ideal world is that, assuming their implementation works and is bug-free, if you're going to run a cryptocurrency service, your first go-to should be to take a roll-up software and just redeploy it. That's sort of why in Starknet, they have this idea called Layer-3, where the idea is that the Layer-2 is really just all the assets locked into the system. And then the Layer-3 are application, an instance for an application. And then it's easy to move funds from one application to another using the Layer-2. So in Starknet division, they're very much hoping people will launch their own instance, but they'll do it as a Layer-3. I only do that because I hate the word Layer-3, but that's how they describe it. So yeah, I think that's the ideal world. They should fork it. Cool. Okay, I don't want to take up much more time because I know Marius has to do his one still. So thank you very much, guys. Those were great questions.
Thank you very much, Patrick, for your time and for answering those questions. You are a great presenter, great lecturer. Makes sense for you to be the one like teaching courses to the crypto, the new people to crypto. So thank you for that.